Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Here from University of Singapore. He's a PhD student. He's third year. And he's sort of touring the US along with his advisor in various places, visiting people doing their work, and he's giving this big talk now on verifying safety policies with size properties managed.
Thank you. It's such a great pleasure to be here to talk about my work and maybe get some feedback. What I'll talk today is how to combine size properties and alias controls to do software verifying of safety policies. This is joint work done in University of Singapore, and I will start up by giving some backgrounds on what size analysis have been used previously. And it has been used for array-bound check elimination, for data structure invariance, and for termination analysis and space complexity. Most of the program analysis have been done are for declarative languages and for restricted imperative languages. The restriction comes from the fact that the data structures are immutable. So the properties that you want to track at static time are also immutable. Our goal, on the other hand, is to do static verification for object-based programs. And the main challenges in this context are that objects may mutate, and at the same time, they may be aliased. So our approach is to use both size analysis and alias control to specify and verify various safety policies. The analysis is based on a type system where we have annotated types. So here we have the underlying class type together with some size properties which represent the annotation. And the properties that this annotation capture are values. So for example, for a Boolean type with its annotation B, we can capture the value true by the constraint on the right-hand side and value false by the constraint B equal to 0. So the Boolean is really encoded as an integer in our constraints. Also for an integer type, its annotation is reflecting the value that the variable has. We may also have size properties that capture length of data structures. So for example, for an array, S would capture the size of the array, which is immutable. Then we would have N to capture the number of nodes in the list. And for tree, we may capture the number of nodes as well via S, and the height of the tree via H.
So your values there, are they just singleton values that the Boolean is true across these integers 5, or are they actually sets?
They are singleton values. For such a system, methods are annotated with size properties. So first we have the argument list, which contains annotated types denoted by tau. And the user will give two formulas, a precondition for safety that specifies in what conditions the method can be executed without any violation, and a postcondition that relates the input, the parameter, with the output, the return variable. Some simpler examples are here with an add method that takes two integers as arguments with their sizes a and b, and it returns also an integer. Then the precondition in this case can be annotated as true, and the postcondition captures the relation between the sizes of the two arguments and the result. The body is indicated in black at the end here. An example of how to use the safety precondition is for a function that would access an element in an array. So the function sub takes as arguments an array A annotated with its size and also an index. And the precondition requires that the index is in bound, so it's positive but smaller than the size of the array. One more interesting example is to specify an AVL tree which would have two size properties that we would like to capture. S captures the number of nodes in the tree, and H is the height of the tree. We are capturing its class definition using an ADT construct, so we don't use inheritance in this case. What we have here is the type that is being defined, which is the AVL tree together with its two size properties and the S and H. Then we have fields for this class definition. This denotes the element value. Then the left subtree together with its size properties, S1 and H1, and also the right subtree. So these are the fields in the object. Then there are two formulas. The first one is the size definition that relates the sizes of the fields with the sizes of the object. So the number of nodes in the tree, S, is related to 1, indicating the root, plus the number of nodes in the left subtree, plus the number of nodes in the right subtree. Then the height is also defined as 1, corresponding to the level of the root, plus the maximum between the height of the two subtrees. This is the size definition formula, and we are capturing separately the invariant for this AVL tree, which specifies practically the fact that the tree is height balanced. So the difference between the heights of the two subtrees is bounded by 1. And this invariant is supposed to hold for all the objects in corresponding to this class. We may also have methods in this class definition, and this is an example of a node insertion method that takes an AVL tree and a integer node to be inserted in the tree. And we are capturing the fact that the AVL invariant is still preserved after you insert the node. So the body of the node insertion method would contain the rebalancing of the tree, and the property is preserved after the node insertion. Note also the postcondition, which is using prime notation. So this would indicate the fact that the new size of the tree is the old size of the tree plus 1, the node that is inserted. And there's also a change in the height of the tree, which may or may not grow with 1, depending on which branch you are inserting the node. This is an involved example. I will use a simpler one to show what problems we encountered for this kind of analysis. And this is a definition for a list data structure, where the size property n captures the number of nodes in the list. And we have a next field that corresponds to the tail of the list. The size definition links the size of the list with the size of the tail. And we have a method to update the next field of the list. So it takes as argument, these are practically static methods. So the first argument corresponds to the list that you want to update, x, and the second one, y, is the list that you want to assign to the next field. So in this case, the precondition might require the fact that the first argument is non-null. Null is captured with size 0. The rest of the property is derived inductively. Then the postcondition captures how the size of the list changes. The fact that the new value is related to L plus 1. There are problems for doing this due to aliasing, and this is an example to show what is the problem if we are aiming to do this analysis locally for each statement. This statement would create a list with two elements in it, and the size is mentioned in the right-hand side, the size that the type system tracks. Then let's say we create an alias to the same object. So now we have B and A pointing to the same object value, and their size properties are related as well. And we update the next field of one reference to point to null. Then in this case, since the analysis is done locally for each statement, y would be updated, its size will be 1, but x is still unchanged because we have no way of tracking the fact that y and x are really pointing to the same object. So summing up all this size relation, we will get to an unsound conclusion where the sizes of x and y differ even though they are pointing to the same object. There are various approaches to the aliasing problem, and we are aiming for a modular approach that would allow us to track these sizes local for each statement. And we adopted a set of annotation that capture immutability.
Back up first slide.
Sure. So what would happen here is that when we have a call to the set next, then the post condition which is captured here would be applied on the current state, but this doesn't specify how the other references would change. So
is that the right post condition, or n is greater than 0, n equals 1 plus L?
on top we have the size definition, and this is the invariant for the list. So the number of nodes is always positive. What I forgot to mention is that we have also to define the size of the null constructor, which is 0. So when we have a list with one element, then its size would be correspondingly 1. So this is not like a precondition. The precondition is here, and it specifies that because you are accessing the field next without checking whether X is null or not, we can encode this as a precondition.
Okay.
Coming back to the set of annotation that we are using, it's summarized here. So each reference is marked with either of these 4 alias controls. There is a read-only annotation that indicates that the reference corresponds to the same object, so it's related to the final modifier from Java. Then we have unique annotation that corresponds to the sole reference to an object. We have a shared annotation that may be globally aliased, and we don't aim to capture any properties on aliasing for that reference. And we have a landing annotation that allows a unique parameter to be temporarily lent from caller to callee. Let me give some examples on how these are used for size tracking. And I have 2 examples on how to have a list definition. Here we have a list with a read-only tail. So note that the annotation for aliasing is captured using this notation. So we have the underlying type, the class type, the properties, and the alias control after an @ sign. In this case, what will really happen is that the data structure corresponds to a functional list where you are not allowed to update its next field. So the references to the list are freely shareable, and the type system can track their size properties since this is immutable. The type system would also disallow assignment to the next field because of its read-only annotation. So this would give a type error in case it's used. But assignments to other fields are allowed since reassigning the value field does not influence the size property of the list. Another example for a mutable list is where the annotation is unique so that the size property becomes mutable. In this case, the type system checks how uniqueness is consumed. So this is an example where X and Y are 2 unique references. And the assignment statement that we have on the 3rd line over here is really passing the unique reference from Y to X, and Y will not be allowed to be accessed later until it is reassigned. Using this, assignments to the next field can be tracked. Practically, we have just a unique reference to an object which is allowed to update the state of the object. We're also using a landing annotation that is slightly different from the length many annotation used in other works. There are 2 properties that the type system ensures on this kind of annotation. Firstly, the value does not escape the method. And secondly, the reference has exclusive access to the object. So we have an example of a destructive append function that takes 2 lists as arguments, xs and ys. It calls itself recursively to traverse the first list, and when it reaches the end of the first list, it's going to do the assignment. So ys is assigning to the next field of xs. The landing annotation is transitive, so the unique reference can be passed on further. For example, if we have this call, append can count on the fact that xs.next is also a candidate for landing. And this practically means that the first argument is both length and unique as well. For the second argument, note that its uniqueness is consumed since you are copying it to a field of another data structure. the way that this can be used is given the signature of the append function. We may have two unique references, x and y, and a call to this append function with these two arguments. The uniqueness of y is consumed since it is copied into the heap, and the uniqueness of x is length but is retrieved back by the caller. So what happens is that you can still use x uniquely as before, but an access to y would be deemed unsound by the type system. We are using this alias control to classify size variables. So we've seen types that are annotated with size properties, and these size properties are classified into three groups. First, we have the size immutable variables, which are freely shared. Then we have trackable size variables that are mutable and unique. And we also have non-trackable size properties, which are mutable and also globally aliased. So the type system cannot check those and track those at static time. More importantly, we need to remark the fact that object size variable mutability depends on field size variable mutability. That's what we've seen in the examples before, where, for example, you have the tail of the list, and whether the size property is mutable or not influences the size property for the whole list. This is an example where we can see that unique mutable properties do not always correspond to unique references. So we have the pair data structure with two fields. We have first and second, which are primitive integers. And the second field is not allowed to be updated, so it's annotated with a read-only annotation. The two properties of the pair relate exactly to the properties of its two fields. So we have P1 equal S1 and P2 equal S2. We also have a method that updates the first field. So it takes a pair and a new integer value to be assigned to this field. Let's see how the object itself is characterized and what are its size properties. And we'll start up with the two fields. So we have an integer, which is a primitive value. And what we have in red here are the three sets, which are corresponding to immutable, mutable but trackable, and non-trackable. So S1 is immutable because this is a primitive value. And it's stored into the first location corresponding to the field, which is shared. So the type system will classify S1 as being mutable, since you are allowed to update the value. And correspondingly, we have the second field, which, since it's annotated with the read-only alias control, its size property remains immutable. Given the size definition, we can relate the size of the fields with the size of the object. And this is the whole pair object, where P1 is mutable, as it was S1 for its corresponding field, and P2 is immutable, as it was S2 for its corresponding field. So now it really matters what kind of references we have to this object, whether they are unique or not. They would further make these things become untrackable, maybe. So one example is if we have a unique reference to this object, and what will happen in this case is that for the unique reference that we have, the immutable property becomes mutable. Note that R1 is related to P1, R2 is related to P2. So practically both size properties are trackable in this case. But this counts on the fact that the annotation for the parameter is unique, is length and unique as well. So you need a unique reference for this. And since both of them are trackable, the post condition would capture their new values. P2 is unchanged, P1 is changed to the size of its second argument. There is also the possibility that the set first is annotated with a shared alias control. And in this case, some client code would be able to create two references to the same pair object, M and N, and call set first on either of these two references. So what we practically have are two shared references. And in this case, M1 corresponding to S1 property of its first field becomes untrackable, and it's only M2 that is trackable. So we used the combination of immutability and uniqueness annotation so that all the size variables of an object can be classified as either trackable or non-trackable. So practically the user, when it declares its data structure, will specify the alias control, and then the type system infers what it can and gives up on the other cases.
So can you go back to the unique one, because I didn't quite understand that one.
So what?
Are 1 and R2 both mutable?
The whole algorithmic way of deriving these properties is in the paper, but what it happens for a unique reference is that the immutable properties becomes mutable. This is because you have a unique reference and you can update the corresponding fields.
But the field is still marked as read-only, right?
Yes, this is true, but
So you can
what?
still modify it?
Yes, in this case, so.
Okay.
This is due to the fact that it corresponds to a primitive value. So if instead, I guess another example would be a pair with 2 boxed integers.
Sure. I'm just wondering why the read-only property gets overridden by the uniqueness property of the pair. But don't worry about it.
So with this example, I will go on to present the kernel language on which we are specifying our analysis, and how we do specify safety protocols in this small language. Then there are some key issues related to the type system that we are using for verification, and I will conclude with some implementation details. So this is the kernel language, where we have the source program containing class definition, denoted here, and method definition. Then the class definition are given using an ADT construct. This defines the class Cn with its corresponding size annotation. We have size definition and size invariant, as we've seen in the previous examples. And we have fields as methods as well. The methods have precondition and postcondition over the size of its arguments. And all the formulas are captured using Pressburger constraints, where we have conjunctions and disjunction over linear inequalities. The types are annotated, so we have types with size property and with alias control. And the alias control are one of the 4 cases that we've seen before. And the language is a small expression-oriented language that allows our analysis to be easily formalized. Besides constants and assignment, conditional and object declaration, we also have a special construct bind, which I will cover in the following slides. For loops, we encode them using tail recursive functions. This is only for the analysis purpose. So the problem that motivates us to have a bind construct is the fact that field access relates an object with only one field. So it is bad for size relation that hold across multiple fields. This is the class definition for the tree with 2 subtrees over here, where the size definition relates the size of the tree with the sizes of its 2 subtrees. What would happen is that if we have T, a reference to a tree, and L, another reference to a tree, if we have such an assignment, then the new size of L, B prime, is related to the size of T, the big tree, from which we have to subtract 1 corresponding to the root, and also the size of the right subtree. But the problem is that the type system does not have access to the size of the right subtree, so in fact what it can do is to quantify over the size of the right subtree, which practically disallows tracking relation across multiple fields. So this is an example which uses field access that is doing node insertion. So it takes a tree and an integer, and the post condition would unfortunately capture just the fact that the integer argument is unchanged, but not the fact that the size of the tree is increased by 1 after you insert a node in the tree. And this is because in different branches, the field access relates the object with only one single field, and the size definition relation cannot be enforced. The bind construct relates an object with multiple fields, so it brings variables corresponding to the fields in scope. It's similar to pattern matching. It takes T as the reference to the tree, and it has V, L, and R as synonym for the three fields in the tree. Using this, V, L, and R can be used to do updates on the state of the object in this scope. And furthermore, their sizes can be related using a size constraint, as it's done on the last line. And this is how we can convert the example using the bind construct. The bind construct is inserted at the method boundary. And what it does is that it consumes the reference to the tree object, but allows access direct to the fields, W, L, and R, corresponding to the value, the left subtree and the right subtree. And now the type system can capture the fact that the increase by 1 is done both on the left subtree. So what would happen here is that the integer is compared with the value of the root element. And in case it's smaller, we would do the insertion in the left subtree. In the other case, we would do the insertion in the right subtree. But on each case, the increase in size is by 1, and it can be easily captured in the postcondition as well. Here is how we are specifying safety policies in our language. One popular approach is to specify safety policy using finite state machines. Our approach is to really encode the protocol using ADTs and specify via size invariant of the object and the preconditions for the methods. Some benefits is that we are able to capture relational properties between different size annotation, and also we have infinite state policies that can be specified as well. So this is an example of a file protocol that is specified using a finite state automata. The safety policy to be enforced is that read and writes are performed only after a successful open operation. In this case, the automata state corresponds to the file state, so we have the uninitialized state represented by the 1 integer. After successful open, the state of the file becomes open and read and writes can be safely executed. Later, after the close operation, the file state becomes closed. We would also want to capture the fact that the open can be unsuccessful, and in this case, the state of the file remains uninitialized, so that you would need to open it at a later stage. This is how to specify it using size type typing. So the type to be defined is a file with its size property indicating exactly the state of the file as. And S is mutable, as it's allowed to change from one state to another. The invariant specifies the allowed states, which are represented as integers, so the allowed states are between 1 and 3. We have methods corresponding to each transition in the automata. The first one is an open method that corresponds to that transition. And the postcondition captures here a successful file opening. So the open method returns a Boolean flag, and the size of this Boolean relates to the new state of the file. So if the Boolean is true, then the state of the file will be true, which means open. And via disjunction, we capture the other case where if the Boolean is false, then the state of the file remains unchanged and it's uninitialized. Furthermore, there are some other examples for primitives. In this example, read and close require a file in open state. So this is specified in the precondition. And close will change the state of the file to become closed. So it's just s prime equal to 3. There are more functions in the ADT corresponding to all the transition in the automata. This is another example of a bounded buffer where its state cannot be directly encoded using a finite state automata. The safety policy is that the buffer should not under nor overflow, and the state is captured as two size properties. So what we have is a bounded buffer with a fixed capacity, and we are adding and removing elements from the buffer. So the number of elements in the buffer itself is mutable. So S would capture the number of elements currently in the buffer, and C represents the capacity, which is immutable. The reason why this cannot be captured directly using the finite state automata is that the size of the buffer is not known at compile time. So it's a parameter for this protocol, and it's symbolic. So really, the state that we have here practically unveils to a number of states where C is unchanged, the capacity of the buffer doesn't change, and the number of elements is varying between 0 and n, which is the parameter for the protocol. There are 3 transitions. The first one, which initializes the buffer, would require that n is positive and will initialize, so we have the pre and the post condition here. The precondition requires n to be positive, and the post condition captures the capacity as being equal to n, and the fact that the buffer is initially empty, so S is equal to 0. Then we have the add primitive, which has as precondition S being smaller than C, which is to guard against buffer overflow. So when you add an element to the buffer, you need to be sure that there is at least one empty slot in the buffer. And for the get primitive, the precondition requires that there is at least one element in the buffer so that you can remove it from the buffer. What I've shown in the previous slide is the fact that of the ADT guarantees that the clients are using the buffer safely. But furthermore, there is a concern about how the buffer is implemented, whether it's implemented safely or not. So for the bounded buffer, it may be implemented using a cyclic array, and using arrays gives rise to a safety policies that needs to enforce the fact that you have no array bounds violation. And our type system checks for this as well. So practically we have ADTs that are built on top of other ADTs so that the data structures can be composed modularly. Furthermore, we are using the ADT so that the protocol can be specified. So we do not allow field access from outside of the current ADT. Field access can be done only using accessor methods. So in this case, the precondition and the invariant completely specify the protocol to access this current resource. I will go on to present a simplified form of our type system. So here we have the type judgment and the expression to type check here. The type environment maps program variables to annotated types, and we have a pre-state and a post-state that relate the annotation in these types. The type judgment is simplified. The one in the paper would also check for uniqueness. So you need to know how unique references are consumed. This is the type rule for the conditional, which would proceed by checking this statement. And the first thing is to retrieve the type of the test variable v from the environment, which better be a Boolean. Its size annotation, b, will influence what branch is taken. So the type system would check the expression corresponding to the then branch, e1, and this is done on a pre-state that assumes that b is equal to 1. This is what's happening when the conditional is true, the then branch is analyzed. And for the else branch, the pre-state contains the fact that the flag is really false, so b is equal to 0. There are post-states corresponding to both branches, and they are combined using this junction to get the post-state for the whole statement, which is delta 3. So this is how the path sensitivity is captured in the type system. And this is the rule that shows how preconditions are enforced at static time. So if we have a call to the method mn with its corresponding arguments, the method declaration is retrieved from the program over here together with the formal arguments. Its pre and post condition is declared by the user. Furthermore, types are retrieved from the environment for actual parameters, and we construct a substitution from formal to actual parameters. This substitution row is used to check the precondition, and this is done using the current state, delta. Then the post condition is composed with the current pre-state to give the post state for the call. The type system is shown to be correct in the paper, and this is done using two normal properties, preservation and progress. And what this really shows is that safety policies are guaranteed for well-typed program. In other words, all the preconditions are obeyed by the code, and this can be shown statically. The implementation, we've built a prototype using Haskell language, specifically Glasgow Haskell compiler, and we are using the Omega solver to deal with the Pressburger constraints. The source language is a Java-like language without concurrency nor exceptions, and we wanted to check on two things related to how viable the method is. It turned out that the verification is sufficiently fast, and this is due to modular type checking, where each ADT can be checked separately. Actually, each method can also be analyzed in the same manner. And we try to quantify the size of the annotation that the user has to provide, and we consider this to be bearable, even though a burden on the programmer. Related work divides on two areas. First is size analysis, which have been done mostly for immutable data structure, and alias control that have been previously used for program reasoning as well. There are other approaches to verification as well, which has been done in the context of a finite type state approach in Volt or Fugue language. There are also approaches using theorem proving. One example is the extended static checker, which aims to do also modular checking, but it's maybe unsound due to alias assumption on the parameters of each method. And one approach using model checking is the Boger model checker, which deals with language that have concurrency and also exceptions in the language, but is able to do the checking for the whole program. And it's also used for partial programs, but in this case, the user needs to provide a test harness, which is really like a driver that would show what are the cases that can be checked, but not all can be done symbolically. Just to conclude the talk, this is a summary. So we were aiming to formulate a relational size analysis that is precise for verification of object-based programs. We are using alias controls to track mutable size properties, and the goal was to do automatic verification for safety policies and data invariants. The future work is lying in the inference of alias and size annotation for methods. So this would assume that the user is willing to give annotations for ADTs, which will encode the protocols, but we would try to infer the annotation for the methods. And this concludes my talk. If you have any questions, please.
So a couple of questions. First of all, going back to the bind construct, you have, in this case, you had a pair, so you did bind with, I think, 3 properties. How does that relate to inheritance? So, example, if you had, instead of being a pair, if you had a subclass of pair that's a triple that adds a 3rd field, how does bind work with that?
I guess we would need some similar construct there as well. So indeed, for pair or for tree, we use bind. For a list data structure, we don't use it because the size relates only to one field. So this was the example before. There, bind is not to be used. But let's say if we have a triple that inherits from a pair, then the triple would have a lot of fields. Some of them are inherited from the pair. Then I guess to access them, you also need to use, at least in our case, a bind construct. The reason that we don't have inheritance is that, at least for the application that we were trying to solve, it didn't seem necessary. But for object-oriented languages, certainly you would need to deal with that.
Also, you don't deal with inheritance at all? I missed that.
No. Yes?
So my question relates to sort of your choice of what you're tracking and what you're not tracking. So in your examples at the beginning where you sort of assign y to x and then say, so why is it that that you're not tracking local alias? Because that's very easy. I mean, tracking it across procedure boundaries and data structures is complicated, but locally it's very easy to do. So why did you choose to take the approach that you took?
So one restriction that we have is, for example, for the landing, which is unique landing as opposed to multiple landing used by others. I guess this just simplifies our type formulation. But what we really want to do is to infer these annotations. So in that case, so we try to restrict it so that the size properties can be easily tracked. But the fact that the unique landing is to be provided by the user, I wouldn't see it as a very big restriction. Because if you have multiple landing, you can do some prior analysis so that you convert it to unique landing.
Okay, so my other question had to do with your formalism for state updates. So I'm a little confused as to how you model the state. So you basically, the size annotations on the types are invariant. That is, once a particular value has a particular type, the type never changes, right? All the changes are the constraints over those size variables. Is that correct?
I guess there are not sufficient details, I'm sorry, here for the type judgment. So what we have in delta is really a relation to deal with, let's say we have E containing a reference to an array. No, an array is not a good example, something that changes, the size of a list. And its size annotation is n. Then delta would contain a relation between n and n prime, which is allowed to change. So for example, it would say that n prime is equal to n plus something.
Right.
And the post state relates how n prime is also corresponding to the beginning of the current method.
But my question is about gamma, because gamma contains the mapping that says, well, my variable L has type list of n, right? And that is not changing. So therefore, even in the post state, L has still type list of n.
Yes.
Right? And so the only thing that changes in some sense in your formalism is the set of constraints you have over n. Is that correct?
Yes.
So in some sense, whenever I mutate something, I have to throw away all my constraints and then kind of rebuild constraints that are still valid after this point. Is that correct?
I wouldn't say that we throw it away, because
Logically, that's what you have to do, right?
we update the primes. So let's say we have n prime equal to n plus 1 here, and we have E that adds one node to the list. Then n prime equal to n plus 1, n prime is quantified away, and the new n prime that comes in is going to be equal to the old value plus one more, so n plus 2.
But then you rename everything to the original.
Yes, exactly. So there is a renaming going on.
So that's kind of what I'm asking about. So I find that it's sort of a strange way to do this. Is there some advantage in doing it that way rather than actually changing? Because the problem with it is that a name like n, which appears in a type, is not actually invariant. And usually you like to have these names and types be invariant. Symbolic values, they're always the same. But in your formalism, they're not. They're actually changing from program to program. They're more like program variables, right? Where there's an underlying store model like a stack. But I don't see this in your formalism, so I'm a little confused about why you chose to formalize it that way.
I will try to answer. If not, then maybe we can discuss further. So delta is relating some state with the current state, and it encodes the relation between this point and the other point. It's important to keep the starting state as well, because the delta is relational and it always relates to the symbolic variables at that point. So we need the old value as well. It's not just that n prime becomes from n plus 1, n plus 2, but it may be m plus 1 and the m doesn't change. So it relates to a value at a specific program point.
I see. So you always actually, so for each symbolic name in the type environment, you actually have two variables, n
Yes.
is prime, and n is somehow, let's say, the beginning of time or method, and the primed one is the current value. Is that?
Yes, exactly. Yes.
Thank you.
So have you considered numeric overflow at all?
No, I came across some very interesting work done by a student of Gregory Morissette, but we haven't considered that.
So what would happen if you added type quantification to your system? Have you got that?
Type qualification.
Quantification, yes.
Type quantification.
I noticed, for example, that you gave that example where you needed to have different mutability constraints on a variable, or you want different mutability constraints on an abstract data type. And you could think about quantifying that abstract data type.
Let me see whether I relate correctly to the set first method in the pair example here, where we might have length or shared.
You could think of allowing pair to be a polymer type.
Yes. We haven't really done this here. The way I see it is that a method would have only one implementation, but it may have different type signatures. So in this case, depending on what is the alias control for this argument, the size property that can be tracked changes. So actually it would be a disjunction between different size post conditions.
Okay.
I don't know whether I answered your question.
So what do you think that, I mean, okay, so you think it would be fairly straightforward to actually add the polymorphic types?
Yes, the thing is that the alias controls are somehow restricted, so it's either unique or shared, and we have length to close the gap. But it's not really that you are willing to say that this is alias with that static name or with the other static name. In that case, it might be most likely more complicated. But in this case, for example, here you would have just two cases, not more than this. And certainly, if you have more arguments which are interesting.
Okay, thanks.
Any questions? Well, let's thank the speaker.
Thank you very much.
Anybody wants to talk to them? Well, let me know.
Okay.
Maybe you guys want to talk.
Yeah.
Thanks for coming.
What wants to